Hello. This is a video that I hope it's going to be short. It's just a video of how to generate the models, the output models from the DAP analysis. I, I explained the other day that there is an entry in the YAM file. Let's repeat that. If you open the YAM file, there is an entry that controls if you want to store or not the output models. The output models is a set of models that comprise the different analyses, like the model for the stellar component, the model for the Gaussian, so for the analysis of the emission lines using Gaussian functions, the somehow reconstructed model for the non-parametric analysis, and the Gaussians. There are two models: the first analysis and the second analysis, and then there are another intermediate spectra that could be useful, like for example the spectra resulting from subtracting the original spectra to the stellar component. So it's a kind of a gas pure plus noise spectra. There is also the opposite. If you subtract the emission lines, and all this was controlled or is controlled by an entry that is named dump model. That when it's set to true and you run the analysis, then in the output directory, like this one, it will appear a file that is considerably large, and this file mm, comprise all these models for each individual spectra. So the shape of this is a FITS file that contains it's a cube, and each slice of the cube correspond to the different models for each fiber that has been analyzed. Let's see if it managed to open the cube. So when you set this parameter to true, then you don't require to do nothing more. But that create huge files because it's replicating the original data, raw stack spectra, plus all the models. And therefore, the file is, as you can see here, it's considerably large. That's like 13 gigabytes or something like that. No, it's yeah, something like that. So if you are short of space and you are not, you don't need the output model, or you don't need the output model for all the data you analyze, you don't need to create that output, and maybe you want to create later on. To create later on, you have two options. One is to run this notebook, the lvm-dap-gen-out-mod that we include in the LVM-dap distribution, and running this model. Sorry, this script. You can't. Sorry, you can't generate the model. This is the most easy option because it's going to read the information in the YAM file directly from the header, from the extension. There is an extension, that is an extension, the DAP, that contains the information of the YAM file. However, it has the inconvenience that if I run the model in one computer using some local directories for defining where to store, where to read the RCCPs for like these entries that I explained the other day. And this is pointing to local directories, then you are not going to be able to run this script without modification because you need to modify these entries. Is that why it's sometimes more easy to run the command line? Because in the command line a version of this script that has the same name, lvm-dap-gen-out-mod, so lvm-dap generated output model. This script is going to ask you for an additional entry in the notebook. You just need the DAP file, but in the script version, the standalone version, it's going to ask you for the DAP file for a label, if you can change the name of the output somehow, and the YAM file. And what's the advantage of that? The advantage is that if you have the version of the YAM file that has been with which has been created the analysis, and you chain of computer, you can chain these entries, and then you can run the script. Um, so I'm going to show you, although I started with a notebook, I'm going to show you how to run this script because I started before. It takes a while because to go through all the spectra to analyze the models. So first thing is that you need just the LVM file, the original file that has been analyzed, the output table generated by the DAP label to put a certain name, and the configuration file. And that configuration file, that is the same information that is included in the info header, info extension of the DAP file. The advantage that since this is a text file, you can edit very easily the directories. So that in this way you have to chain where you want to have the output, where is installed the LVM code, where are the SCCP libraries. So all these entries has to be modified by you in order to run this script. Once you modify that, then you run the script, and I have been running that for a while. It's now in the last steps, just to show you that there is no trick in here. I'm going to enlarge that a little. The inputs, for me it was more easy because I ran um, uh, this analysis in this particular computer, but actually not exactly. I This is the call for um, the call for the analysis that I have been done. Okay, and this for generation of the code. So this is the script. This is the LVMS frame that has been analyzed. This is the output of the analysis, and that's just to indicate you this analysis has been done in another computer. That's named Ophelia. That's a server that we run things, and I'm running this script in my laptop. So this YAM file is pointing to the location of the local directories in this computer. So that's what you have to edit to run that. Of course, I'm not going to run that again. It was the label and the YAM file. I'm not going to run that again because it takes a while, and it's basically reading the input, reading the information of the emission lines, and it's going through all the spectra that has been analyzed. And let's see, now it's writing the results. And actually, the results are going to be written in a different directory than the directory that it was running the original computer. So if I try to read this directory, there should be an output file that um, I think is that, let's see if this was the name. It's basically now writing the results. It takes a while. Yeah. So you have to wait for a while. So and it's written. It's going to be written in here. For whatever reason, it's written in the local directory. You see, that's the label was test, and now it's writing the result. So yeah, that's something to change. It's written in the it's going to be written in the local directory. So it takes a while. Let's wait for a while it's doing that. Let's go to the other option that is basically the notebook. And in the notebook, you also have to change this local directory path because it's going to look for the directory where that is stored in the info extension, and it's where it was stored and where it was run in somewhere computer. No, so let's start this notebook. Um, we select the right kernel. Um, okay, it's a bit slow, and that's just important what is required. That's not too relevant. And in here is where we define the input parameters. So we need the S frame, okay? We need the label, and we need the DAP file. Now we don't require the YAML file because that information is going to be taken from the DAP itself. But we will need how to modify that. So let's see how this works. So I'm going to comment these three entries. My laptop it's now running the generation of the code of the model, and it's becoming slow. So maybe it's good just to show you how this works. So first, let's try to replicate the same entries just to see that it's exactly the same analysis. This notebook was created based on the standalone script, so it's basically the same code. So we need the name of the okay the LVM frame. Its name, the variable is named in this way for historical reasons, but it's an S frame. Okay, that's not it's not relevant. What? I don't know why it has created that all this test. Let's do again. Okay, then label. I'm going to use a different one, like a notebook test, for instance. Okay, and DAP file is exactly the same DAP file that I showed you before. So it read the variables, and it's going to open the DAP file. Okay, and transform that to a new table. So I'm going to just chain manually, and I'm going to generate just the model for the first 10 spectra. If you want to generate the model for everything, just comment that. That's all. No? But for the speed, now it's going to read the DAP file. Okay. So, and from the 10 first spectra, some of them are not signs in the S frame. Those ones are going to be masked. Of course, it takes a while. Let's see how is the storing of the output still going on. So it's just reading the input files, and now it's going to define the output file. I mean, I personally don't recommend to use the notebook unless for making tests and for knowing how to deal with the script. But the standalone script is much better for doing so. For doing this analysis, it's normally it does not take that much. It's simply because my computer is really taking a hard time. Uh, Even Zoom consumes a lot of memory, by the way. But it's really having a hard time to doing three analysis at the same time. So let's move out of here. Um, okay, still reading. Once you read that, uh, then it's going to define the output file that you don't need to worry about. It's internal things. It's going to read the position table, the real position table. And here is going to trim the spectra considering the number of spectra that we have tell the script to for generating the output model. So these 10 spectra here. Um, if we don't put any range, then it's going to consider all the full spectrum. Okay, some internal computations that are required, and then it's going to generate first the models for the emission lines in the different versions. It's reading the table. That's the easy part because it's a set of Gaussian functions. So it reads the wavelength, the velocity dispersion, the flux, and create a set of Gaussian functions. So that's considerably fast. And then it's going to start reading the coefficients of the decomposition of the stellar analysis from the information in the DAP file. I think it has created, let's see if it's run already, has given an error. No, it's still where it was. That was that, that was that, that was that. It was reading, okay. Configuration files, yeah, 10 spectra, as we said. And now it's making the analysis of the emission lines, and that's pretty fast. And now it's reading the weightage of the decomposition of the stellar analysis, okay? That we can avoid because it was just an information. It's not. Yeah, and here it's what it. Yeah, okay, it crashed because the program was not prepared for making a trimming on the number of spectra to be generated the model. So that's something I will need to chain. So it will work well if it does not. So that's how I can arrange that from into n coefficients. Table ID. That's a broadcast shape. Do that. that's actually a relatively easy thing to do. Um, so yeah. So okay, and X. Let's see. Good. That's a modification live on. That's so that's the kind of things. So that right should be 8. Okay, so therefore we need to trim this. Okay. Okay. I have to put an if because that's only if we modify that. So take that. That should work. And I will update uh, the notebook. So if we make a trim in the number of emission lines, number of fibers to be analyzed, spectra to be for which we want to create the model, then yeah, that I guess it's the way to go. So Copilot is amazing. Somehow, sometimes it's not as efficient that one may expect. So I made a mistake in the induction. So yeah, that's not it's not going to be that easy because the index may change. Well, this will work. Later I have to make a revision on that because I don't think the index will work in the same way. But it's just, I mean, for a test. So now it has gone. It's taken the 8 first results. Now the configuration file, and now in the configuration file, you will see that the input path may not be the one that are required to generate the templates, to generate the models, because as I told you, this is run in a different computer. So if I try to run now to generate the RCP, read the RCP file, it's going to crash because it said that it cannot find that file. And it cannot find that file because it's pointing to the directory of a different computer. Okay? And in the templates are not in here, that directory does not exist. In my local computer, the RCP files are in here, okay? The templates. So therefore, I need to change that directory for this directory. How we do that? Well, that's the good thing of this um, configuration file is that we can just take it here, okay, RCP file, and we said where to find it, okay. So that is required just because we are running the analysis in one computer, and we want to create the model in another computer. And also for the narrow one, that is for the nonlinear parameters, okay, that other it's going to be wrong, yeah, because it's not in this computer. This is exactly the same thing that you need to modify in the YAM file when you run the standalone script. It's exactly the same thing, okay? So now, let's see if that's something that is not right here. And now, of course, if when it's showing that, it has a chain. No, it's not that. It's not that simple. Sorry. Okay, it's how we chain that. Param. It's not in that way. So we have to make the following. Tab param tab config. So I have created a table that's a column that's not what is needed. So I have to say param. When this is equal to SSP file, when param is equal to that param. Let's see if this works. I'm going to try for the just for one. Let's see. This read this. It didn't complain, but let's be absolutely sure that it has changed. What it is? Well, let's. But I better show sadly that parameter. No, no, nothing. Okay, let's show just that. I need to close that. Come on. Hey. Yeah, of course. I didn't write the entire. What it is require. Okay. Why it does not show me the value? Okay, sorry that so it's say. Okay, sorry. I was modifying the was doing the modification in the run in the run array, the run variable. That it's we need to modify this directory. So it's a config the RCP file should point to where it is stored in the local directories, and the recipe NL file should be stored in the should be pointing to the local location of that templates. Then it reads the recipe file, and just to making a test, I just plot the first of the recipes. Um, um, these these other prints are just for test. They are not needed. And Sigma. Okay, so we're all again that we don't need. If it's needed, we will include it. And now it's creating the model. And well, it requires the sigma inst that it was remembering from the other video that there should be one. I don't know why it has not read that from the header. I mean, from the extension. I mean, sigma inst. This is a guess, so it's not really that important. But if not, the program crashes. 1.0. Uh, okay. Yeah. So let's see. Plot. Ooh, he didn't like it. So that was needed. Bring wave, bring wave, bring wave. That's all. Model. Okay, there was an as type here because apparently the former entry was on string. That goes pretty fast because there were only 5 models, 8, sorry, spectra. If they were, we have not trimmed the NY range to 10, from them 8 are signs, then this will have been much slower. As you can see from the from the analysis that was made with the command line in this computer, that it's a very slow computer. It's still analyzing that, and now it's creating the different versions of the different models that are distributed. Let's I'm not going to, well, better I explain them. That's not the first model. It's the 0 is the original data. 1 is the model of the underlying stellar component. 6 is the model of the emission lines analyzed using the Gaussian function in the second analysis. It subtract those models to create some kind of a noise version, and the residuals of the non-perfect matching of the template that we have fitted with the spectra. We create a smooth version of that residual, and that is subtracted. But we store the original model, so you can trace back what has been done. And we have a second model that basically is a model of that will be a model of the stellar component plus the emission lines. The third will be the subtraction of the stellar the original spectra to the stellar model. So that basically means that this is the one that you should use for analysis of the emission lines. Then we repeat we made the opposite. That's the full residual when you subtract that's this 0 minus 1. This is the full residual when you subtract both the emission lines and the stellar component. This is just when you subtract the original data to the gas. So this is an spectra of the model of the emission lines. This is will be an spectra with just the stellar component if you have fitted all the emission lines. And finally, we have another extension that is model 7. It's the analysis yeah, okay. This is the model of the emission lines fitted using the non-parametric or with the parameters derived using the non-parametric fitting. So therefore, this will be a model similar to this one, but with all the emission lines in the long list table with the analysis of the non-parametric properties. So all these, so we have 8 versions of the spectra, and all this is stored in a individual frame that, and we can, of course, plot these models. And you can read also the output if you want. No such a file or directory. You see, that's again, the output directory is relying on the info entry. So therefore, we need to modify also that output directory, and that could be here or on top, just to tell where we want the output to be stored. And that's the modifications that you need to do to run the script in your local computer. So let's see where it's written. Model spectra, fits name is taken out fit file, where it's that was outfit file. Of course, you can modify that here or before. Let's see where it's defined, the out file fit. So it takes, the output path, and that output path is taken from the info extension. And to change that, just to be consistent with the changes we did before in the directories, well, we can put in here and say where we want the output to be. So the config is to override the information that it's in the info extension of the DAP file. So I'm going to put that in a different directory here. Okay. This is, let's look again for that. Now it's going to store in the right directory. This is still writing the super huge file. And of course, it has the label that we put, this notebook test. And well, the file is not that big. It should not take that much, but apparently writing in my disk is getting complex. But okay, let's wait. And as I told you, that then you can read it, and the for each fiber, analyzed fiber, you have one slice, and that so it's stored here. Okay. Of course, it has only 8 outputs because so it's the z-axis correspond to the wavelength direction. The y-axis correspond to the each of the model, no, each of the fibers, sorry, and the x-axis correspond to the different versions of the spectra, the original spectra, the model of stellar population, the model of emission lines, and so on. And actually, this is described in the header. Okay, what to which entry it's which entry correspond to each different of those extensions. So how to manage that? You read the output file, and for each you create a slice. You want to extract each of the models for of each of the extensions for one fiber. You create a slice with the index of the fiber in the y-axis, and then the index in the x-axis will correspond to which model you have been stored, or the original data. And this is exactly what it's doing here. Here I plot this model spectra. Okay, for you can see the x-axis is the different models, and then I make a mean, a median of all the spectra. So you can analyze the integrated spectra, average spectra, or you can plot the models of the average models of generated for each individual spectrum. That's interesting because it's the model, the average model should correspond somehow to the average spectra. Remember that the average model has been fitted to each individual spectra. No? So if we run in this way, um, of course, instead of making an unmin, you change this entry for a fixed index. It's going to show you the spectra corresponding to that particular spectrum fiber. So this is just a simple plot that I created showing the original data. Remember, there are the 10 first fibers, and maybe there are not very strong stars in there, and there are some defects, as you can see here. But that's a zoom on certain emission lines and the comparison of the models with the data, and these are the weak lines that are also fitted. Well, that's just an example, but of course you can change the different entries here, and you will see different versions of the model. So that was all, and again the video, since I made some modifications in the code and so on, the video is much longer than what was anticipated. So sorry for that.